evaluator, right? And we noticed that it was not quite doing the right thing. Actually, I should just type eval, right? So if we say 9 minus 3 minus 2, we get 8 instead of 4, right? Why do you think that is? That's correct. So we're actually doing 9 minus 3 minus 2. Why do you think that happens? Whereas if we were doing 9 minus 3 minus 2, we would get the correct result, right? Why do you think that happens? Yes?
Does consider 3 minus 2 as an expression?
Yes, very good. So remember how we are evaluating right at this level, right? So the expression is a term followed by an expression. So when it looks at this string, it will say, oh, I discovered a term, and now I'm waiting for an expression, right? Now, when the highlighted part becomes an expression and is converted into a tree, we're going to have minus at the top with the children 3 and 2, right? So minus 3 and 2 is going to be lower in the tree than the 9 minus, right? In other words, right, if we look at a tree like this, right, what we would want to have is minus right, so another minus here, and then and 3 and 9 here, and this should be 3, right? This is ideally what we like to have, and there's a 2. But what we actually have is minus yeah, I should have brought a tool to draw. It's gonna be, I actually have one at home. But it looks like this, right? Three, 2. All right, so we have the wrong associativity for minus. It so happens that plus is associative, so it doesn't matter, right? But plus is formally defined as being left associative and not right associative. So we're actually evaluating even the plus wrongly, right? But we're not observing it. So how do we sort this out? Now, one way to sort this out, if we go back to our grammar, which we had at some point, let's see if I can still find it. Here it is. Right? So you might be tempted to say, oh, let's change. Let's do expression plus term. This would solve the problem, right? And indeed it would, right? But if we start from this grammar, we need a different method of implementing the parser, right? The strategy for going from grammar to code that we applied here doesn't hold anymore, because we would have this would be a function immediately calling itself recursively, and it will go into an infinite loop, right? There would be no way to decide up front whether I have this rule or this rule. But there are other ways of building a parser, the so-called LR parsers, which is LR stands for left recursive parsers for left recursive grammars, right? And this is left recursive. The recursion appears at the left, right? So there are such methods. They're essentially quite complicated. There are tools for that. I'm not going to go into either of them. But there's a simple fix for it, right? In our particular case, we have to differentiate between the case when we get an expression from this kind of rule and an expression from this kind of rule, right? Because whenever we get an expression from this kind of rule, right, we have to change the associativity. We have to change the tree. Whereas if we have brackets, we don't have to do that, right? So if we have this situation, we don't have to do it, right? This is the brackets are genuine, right? They change the precedent. So, but you see, the expression, the node returned from this expression, and the node returned from this expression are the same, right? Brackets don't change the tree, but we want the brackets to change the precedent. So then we're going to play one trick. We're going to add to the tree a flag, meaning an integer, that tells us whether the node had brackets or not. Is that clear? We're going to differentiate between nodes that are coming from within brackets and nodes that are not. Okay? So the first thing that we need to do is add a flag here. And flag means int. So flag means a boolean, but remember, booleans don't exist. So as paren. Okay? So notice that when I add this field, actually the program still works fine. We have added something, we have not removed anything. Everything that the program expected to be is still there, right? There's this extra element that nobody uses, but it doesn't hurt to be there. Okay? So when we create a node, we will make sure to create it with aspirand equals false, right? That is 0. Because you see, at this point, we don't know whether we have brackets or not. All we know is that we have term plus minus expression, right? The term plus minus expression. Whether we have brackets or not, we don't know quite yet. Okay? So let's do just that for the time being. Equals 0. Right? Here, the same thing. Okay? And the interesting thing is, what do we do with this result? This result has already been built. There's a has paren flag inside here, right? There is a result arrow has paren, which is probably 0, right? But now we know that there are brackets around this expression. So indeed, we do return the same result, but we know that this result is coming from within brackets. So let's alter this to be 1. Okay? So for the time being, there's nothing more to do. All right? Now, let's look at this rule, right? So we get a left, and then we get a right. Okay? And then actually, sorry. We made this change in factor, right? This is where we made the change. This is the first place where has paren maybe 0, right? So let's look at the place where factor is being returned, which is here, right? So we have factor, so we have a left, we have a right, all right? And the same problem of bad associativity happens for division as well. right? So for instance, if I'm going to say 8 divided by 2 divided by 2, I'm going to get 8, right? Because 2 divided by 2 is performed first, returns 1, right? So we want to do the same thing. So now we're going to return this result only when what? What is an important condition to establish now? So definitely once we reach this place, we will have to return a node. We have discovered, right? But let's add an extra if condition. And when can we do exactly this? Only when I have a bracket in right, right? So if I have a bracket in right, if I have a bracket in right, then this can stay unchanged. You see, the tree, it doesn't make a difference if I have a divided by 2 divided by 2 currently, or a divided by 2 divided by 2, right? They produce the same result because the tree is the same. Brackets or no brackets, currently, brackets or no brackets, currently we have the same tree. That's why we get the same result. But if there's brackets here, the result is actually correct. So we can return this tree only when we have brackets, right? So if right has paren equals, and actually we can leave it like this, right? It's a flag, so it works all right. Okay. So if we don't, what do we do? So now there's a very interesting situation. So I have 8 divided by 2 divided by 2, right? So currently I have this node coming on the left, all right? And then, sorry, I have this tree. So I have this node coming from the left, and I have this node coming from the right. And I don't have brackets here. Okay? This tree is coming like this, right? And we were very tempted to create this link. But what we're going to do now, right, is we're going to put this 8 here, right? And now we're going to perform a rotation. I'm going to put this 2 here. I'm going to put this guy here, and this becomes the root. So we perform a little rotation. Okay? So let's try to make it practically clear that my prospective graph would have been so this is division, right? Division. Let me divide it to 2, and we're going to turn it into division. Division a 2. Let me circle the division. Circle the division so that it's clear that it's a node, right? So we're performing a rotation. So this is what we call result. Typically, this is our left, our right. Okay? So here I'm still going to have the result, and here I'm still going to have the right. Okay? So what we're going to do is I'm going to save this guy somewhere. Right? Then we're going to do right dot right, arrow right equals result. Result, arrow left equals result. Okay? So we're going to do, so left is left, right is right. This guy we have to do it no matter what, so let's take it outside. All right. So actually, we don't have to put anything into a temporary location, right? What we're going to do is result left equals result dot right. Result, let's do it in order. Left equals left. Okay, result dot left equals left. Result right equals right. 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 And return right. Result C equals C. Alright, result has parent equals 0. And this should be it. And we return what? We actually return right. So now the naming is not that great anymore, but let's make sure that it's correct. So I get the left and right. So the result of left is the same, stays the same. The result of right is right dot right. And then we return right. Okay, let's test it. So now we should have solved the division, right? So 8 divided by 2 divided by 2, and the result is 2. Okay? And if I say 8 divided by bracket 2 divided by 2, I'm still going to get something wrong. So, result left stays the same, right? As before. But previously we were doing result dot left equals left. Right? Stays the same. Result arrow right, right, used to be right. But now result arrow right has to be this guy. This is right dot right. Right? So result dot right equals right dot right. Then right dot left equals result. Right dot left equals result. That's what you can do. I knew we missed something. Right dot left equals result. So 8 divided by 2 divided by 2. This doesn't work. But 8 divided by 2 divided by 2 works fine. Alright, so let's see why the bracketed result doesn't work anymore. So 2 divided by 2 is 2. Very interesting. That's the reason. Oh, but there's another thing now. So so right has paren, right doesn't have paren, so it doesn't. I don't need to reset it. So why is 2 divided by 2 equals to 2? 2 minus 2 is 0. If I comment this out, so 2 divided by 2 is 1. So it's coming from here. So if right has parentheses, we do it the old way. So we set it to 0 here. Alright, so I'm going to apply a trick. So single numbers, it doesn't matter whether they have parentheses or not, right? The single numbers don't require rotation no matter what, right? So we're going to pretend that they have parentheses. And that will fix our problem. So 8 divided by 2 divided by 2 is 2. 16 divided by 2 divided by 2. Oh, 16, we can't do 16. Sorry. We're gonna be able to do 16 in a minute. So 9 divided by 3 divided by 3 is 1. All right. And 1 plus 9 divided by 3 divided by 3 is 2. So it seems to be working correctly. So if I still say 1 plus 9 divided by 1 plus 2 divided by 3, this is still 2. Great. So we sorted out division, right? We haven't sorted out the subtraction. 9 minus 3 minus 2 is still 8, right? So we're going to apply the same thing for the next level. Okay, is this okay? Some of you are looking very puzzled. Is this okay? All right. So there's indeed a trick that I played here. So has parentheses, I marked this with 1, right? So maybe the name has parentheses is not quite the right name. I should have said needs rotation, right? So whenever we have the brackets, we don't need rotation. And whenever we have a single number, we don't need rotation, right? But whenever we have a tree containing another subtree, which at the left on the right side has another subtree, and if both of them are minuses, it doesn't matter whether they're minuses or pluses, right? They have to be left associative. Then they need rotation, right? We need to do the rotation. So the has parentheses, it tells us that there's no rotation needed, essentially. So why don't we actually change it? We'll find, replace as parentheses with replace all, done. Okay. So then we have to do exactly the same thing at this level, right? And what we're going to do, because it's exactly the same piece of code, right? We're going to copy this in here. Okay. And this should now work. So 9 minus 3 minus 2, and the result is 5, which is incorrect. So 3 minus 2, we have the same thing. The result is 1. 3 minus 2 minus 1, the result is 1. So there's something wrong with the rotation. So again, which means that there must be something wrong with the division as well. So if I take this out again, dot is 2, but 3 plus 2 plus 1, I get 6. And then there's something wrong with the rotation. So again, let's go again. So we get right and left and right. So result dot left, in this case, result dot left would be 3, right? Result dot right dot right would be 2, so result dot right becomes 2. Right dot left is result. Right dot right stays the same, which would be 1. Result dot C equals C, which is the minus. Yes?
Right equal right to right. Why isn't it right to left?
Good point. Very good. Then here. Very good, Vanessa. That's why you're puzzled, huh? Okay, so where were we? 3 minus 2 minus 1, 0. Okay, so this is what we want. So 3 minus 2 minus 2 minus 1, this is 2. All right. So if we try a complicated expression now, so let's do a multiplication so the result gets very large. For example, 5 times 2 times 5 times 2 divided by, so it would be nice to produce, because we want to produce whole numbers, right? So 9 minus 1 minus 3, so that's 5, divided by 9 minus 2 minus 2, so that's also 5. So we should have 4, right? Ah. So 9 minus 1 minus 3, oops. This is 5. If I put this in brackets, 9 minus 1 minus 3, it's still 5. 5 times 2 times 5 times 2 is 100, correct? So 5 times 2 times 5 times 2 divided by 5 first, and get 20. So 5 times 2 times 5 times 2 divided by 9 minus 2 minus 2, still 20. So if I take this and divide it further, divided by 5, you get 0. So essentially, if I do 5 times 2 times 5 times 2 divided by 5 divided by 5, this is 0, right? And if I just do 5 times 5 divided by 5 divided by 5, now I get 1. So if I say 5 times 2 times 5 times 2, I'm trying to get a small enough example. Now I get 0. Alright, so we're going to continue to debug it, right? So let's learn a new thing about trees, a method we call traverse. So we're going to traverse a struct tree. What is it, tree we call it? Struct node. So we're going to add this method that would help us debug the tree at the end. We want to see what the tree looks like. So if n is not equal to null, then we're going to do printf %c open bracket, and then we're going to say n dot c, and then if n arrow left not equals actually I'm not going to do the bracket, not equal to null. I'm going to do printf, and now I'm going to put a bracket, and now I'm going to do traverse recursively n left, and then I'm going to print a comma, then I'm going to traverse right, then I'm going to get a close bracket. Okay, and then for debugging, we're going to, after having gotten the tree, let's do a traverse tree. Okay, I'm going to run it. You're going to see the output first. So let's do the same thing that was causing us trouble. 5 times 5 times 2 divided by 5 divided by 5. And look at this representation, right? This should show us the tree, and it kind of shows us that the tree is wrong, right? So based on what you see there, based on what you see here, the root is division. I'm just going to circle it. Then I have a star here, right? The star has a 5 here, right? There's another star here. There's another 5 here. There's another division here. There's a 2 and a 5 and finally a 5, right? Which means that there's something wrong with our rotation, right? Our tree should be division 5, division here 5, star. There's 2 stars, right? 5, 5, 2, right? This should be our tree, right? And instead it looks like this. Now, before we go anywhere, let's look at the mathematical traverse and let's understand why it provides that output, right? Because that's an interesting thing, right? So we get a tree. So if the tree is not null, right, I'm going to print the current character, which is this guy, right? So now, my current node might be an operator node or an operand node. How do I know whether it's an operator or an operand? Well, I look at either left or right. If it's not null, then it's an operator. If it's null, it's not an operator. So if it's an operator, I want to open a bracket and print the left subtree, comma, print the right subtree, because this is what we have here. So this is the left subtree, and this is the right subtree, and then we close the comma, right? So we recursively print we print the open bracket, then we recursively print the left subtree, then we print the comma, then we recursively print the right subtree, right? So then we get this representation of the tree, and now we know how the tree looks like inside. And we know for sure that the tree is wrong. So let's see, how much did we get right of it? Right? We only performed rotation here. This last rotation. This is the last rotation that we have performed. Right? And what was our original expression? We didn't have any brackets. So we should have performed rotation at every step. So we should have performed rotation at every step. We should have performed rotation here. I'm starting to understand the problem because, so for instance, if we do this one is correct. So every time we have more than 2 operators, it's gonna bump. Okay, so let's do it step by step. So what are we doing now? So we're essentially, at some point we're going to look at 255, right? So 255 gets 255 here gets rotated correctly. So we're going to have division 2, 5, then this star comes in, right? So we have 5 star and this, right? And this needs to be rotated. But the rotation should put the 5 down here, right? Not here. Okay? So my algorithm is wrong. I remembered it wrong. Alright, let's see if we can fix it quickly. Let's see if we can fix it. So the current rotation will produce R5 instead of that, this y is a point of this y. All right. All right. Before we go into that, because that I'll probably need to think a little bit about. Let's try instead of just accepting digits, let's try to accept full numbers. Okay. So let's leave it the way it is. It works fine for sequences of 2 operators, but not more than that. All right. So what are numbers? Let's go back to our grammar. Right. So here we accept digits, but instead of saying digits, can we just say number here? Right. And then what's number? Digit followed by number, right? Or simply digit. Right? So let's write a function that works exactly the same way, right? So it accepts a digit, it consumes a number, right, from the input, and leaves the current character on the position that follows immediately after the number, right? So and then once we get there, what we want to return is a node containing the number, right? So instead of returning, right, of doing this here, creating the node, because you see we are essentially not in eval. Sorry, not in eval. Here we are essentially creating this node here. So let's write here what we would like to have. So we would like to have result equals number, right? Then return result. So if we can get a number, then we get a number. Otherwise, we get we return now. Okay, and we write a, and actually to group them together, it should be right above eval. Okay, so struct node star number. Okay, so if the current character is a digit, then we are sure to have a number. There may be more digits, but we at least have one number, right? So if that doesn't happen, we can return null. So if where were we? Star P, right? P was our current character, P, right? So if star P not is less than 0, right? Or star P is greater than 9, return null. Okay? Otherwise, we're going to have a number, right? So instead of having a character here, let's have an int value. So we're going to use the the character for operators and the value for numbers, right? So let's return that. So while or for, there's no initialization. Star P. So let's say 0 less than star P and less than or equal, and star P less than 9 and P plus plus, right? And what do we do now? So we have to assemble a result. Actually, we can define a result here, right? And what do we do at every step? Result equals, actually I can say plus equal. Okay? So we are accumulating the result. But actually, I shouldn't just call it result, let's call this value. So now we have the number, but we don't have the node. So we're going to create a node. So struct node star result equals all right, so we have allocated. We're going to say result value result C. So we're going to use a special character, and I'm going to use the @ character to signify the fact that the value is valid. There is a proper value inside. Okay, and result needs rotation equals false. Sorry. Needs rotation should be we we called it wrongly. So if it, because we're essentially saying that it doesn't need rotation, right? When it's 1, it actually doesn't need rotation. So I'm gonna rename it again. I'm gonna call it no rotation, so that it's clear. Replace needs no rotation. All right, so no rotation should be true. Have we left anything out? The result.value, result left equals result right is assigned to null. All right. So this should return us a node having a number. And then this should work fine in returning a tree, right? So now we need to change our evaluation, right? Why is that? Because here we're checking that C is between 0 and 9. That will no longer be the case, right? So when we evaluate, right, actually there's a very simple thing we can do. We can just throw this away, all right? And then we can add in switch here, we can add case at. And we know that we use the at symbol only when the value is correct, right? So in that case, we can return and value. Okay? So we're playing this trick. We're using the at sign as an operator, as a would-be operator that actually indicates the fact that there's a value there. So let's run, see if all right, so if result equals number, this should be this is a warning. What line is it? Line 18. And we should say not equals null, so that it's explicit what we mean. And guess what? Number is also a library function. So we have a name clash, unfortunately. So we're going to have to call it something different. And the easiest thing to do is call it num. And hope that doesn't clash. Where is it? Oh, here. Yeah, num is not good either. Okay. Integer. Usually I try to spend a bit more time. Integer is not good either. All the good names are taken. So so num parse. Okay, this one should work. Num parse and then num parse here. All right, so there's another problem. Actually, I think it's not a library function. So we need to provide a prototype. And then use a fun declared identifier value, which is in line 105. Oh, because this value is declared inside here. So let's declare it outside. And the value. Confirming reach end of non-void function 110. Oh, return result. We forgot. Okay, let's see. If 1, 2 plus 3, 4. We don't catch such a break, do we? So do we get at least 1, 2? No. So let's see if we reach here. So it did return. So it did return, right? So it did. This value is correct. Was produced correctly, right? So then we have allocated struct. Yeah. So this is okay. So remember, struct node star is only 64 bits. It's too small to hold all these values. Okay. So we haven't allocated, by me putting a star here, we haven't allocated enough space because struct node is now quite large. So it has a character, a value, a flag, and 2 pointers inside, right? So it's probably somewhere around 32 bytes at least, probably more than that, right? Then a pointer, which would be this guy, is only 64 bits. Doesn't have enough space to hold all that. So then, when we were doing some of these assignments, we were essentially writing outside the allocated area. Okay, so not better. Yes. Is it when we do the traversal, we only print the character, right? So now we're not printing the value. But so we're going to see a lot of ats. So the traversal works. I think the traversal works. And then the evaluation might not work. Yes, and if the evaluation doesn't work, oh, I wonder how it worked previously. Oh, it did work previously because we right, we should protect against null. If so, we should say left equals 0 if n left not equals null, then left equals eval n left. That was the reason why we were getting the segmentation error. Okay, so it works for 12. Let me just remove this. So 10 plus 20, 30, yay. 10 plus 20 times 5, 150. Not good. How did we get it? Oh, 30 times 5. I thought that was sorted out. So when we were doing 1 plus 2 times 5, oh, it's because of the rotation now. This rotation is not good business. Right, so there is another condition that we need to add off the bat, right? So we're going to say if right no rotation, or right C, so we are at the level of the term, right? So whenever I have a term which is a plus, right, plus or minus, if on the right I have star or division, then I also don't need to perform the rotation, right? Because it's a higher precedence, a higher precedence uh, operator. So not equal star, or actually it's an n here. E not equal division. Okay. There's an extra bracket that I forgot about. So again, 1 plus 2 times 5, and we haven't fixed anything. Oh, I'm sorry. This doesn't belong here. I'm very sorry. This belongs to the expression. So 1 plus 2 times 5. And then it's not different, it's equal. Okay, finally. All right, so 10 plus 20 times 5. 110. Yay. Okay, let's fix. Let's try to fix very quickly. Let's try to fix the rotation problem, right? So what we need to do is I'm gonna draw one thing I was doing while I was solving this one. The last problem was in my mind. I was trying to fix a rotation problem. So let's say we have the following configuration, right? I'm going to just use minuses because it's easier, which has already been, it's like this because we already have done a rotation. So we have 10, 2, 3, right? So it's like this because we already have rotated it, right? And now the temptation is to put a 20 minus here, right? But the 20 actually needs to go down here, right? Everybody understand this? So what do we want to do is, instead of moving the right to this guy, we want to move the rightmost right. Okay? So here, actually, it can be a much longer one. 10, 1. Right? So what we need to do is to move the rightmost right. So this is my result. This is my right. Right? So previously what we would do was result dot right equals right dot left. Right? So now result dot right equals rightmost right of right. Rightmost of right. Right? So rightmost of right is this. How do we find rightmost of right? I'm going to do a while loop, go down here, find it. Very good. Very good. The rightmost of left. Okay? So all right. So the easiest way to do that is to write a separate function. So we're going to write it here. So we're going to have a struct node star rightmost of star n. Right. So while n left, not actually I'm going to do this. Left, left, not equals null. Right? So I want to find this guy. The 10 is also a node as null, right? So I want to find this guy. So I'm going to go down to the left until the left of the left is null. I want to be at this null, right? Left of the left is null. And again, I should be using for instead of while. equals n arrow left. Return n. Okay. So let's see how we use this. So we want to use it right here. And again, so result left stays at left. Result right should be leftmost of right. Most of right. Right dot left is result. Result dot C is C. Result is no location. And we should do the same thing here. Result dot right is the leftmost of right. So let's see if this works. And again, we need to provide a prototype. So strangely, this is not necessary. I can leave it out, and there's not gonna be a warning.
Isn't it function of
Yeah, it's probably there is. What do you mean rightmost?
I think on the default there's this function called rightmost. Just to know the rightmost.
But I want leftmost, right? Let me just make sure that it's been a bit of a long day. And then we used it correctly, right? And leftmost and left. Okay, cool. So let's see. 10 minus 1 minus 2 minus 3 minus 4. Well, that is 12. So let's see. 10 minus 1 minus 2 minus. So let's see if this still works. No, it doesn't. 10 minus 1, does it work? Right, wonderful. 10 minus 1 minus 2 is 11. So if in this case, I should stay on the same node, right? So if here I have in right, going back to what I had before, read right, left. That works, this works correctly, right? No. All right, in traversing, let's do the traversing properly. Yeah, this is quotes. So 10 minus 1 minus 2. So it is not rotated. Ten minus 1 minus 2. This is correct. If I say 10 minus 1 minus 2, this is correct. So when I go here, in the expression, right? So I should have no rotation. I should have no rotation because we're sending 1 from num_parse, right? Yes. So we have no rotation. Write.c should be minus, so this is false. If write no rotation, if this is true, right? Because it's what do we do with a no rotation? I'm completely confused. Do we want rotation or not? So we don't want rotation for brackets, and we don't want rotation for numbers, right? So when we have brackets, it says indeed no rotation, and when we have numbers, which is indeed no rotation, right? Everything else is rotation. So then the minus on the left, sorry, the minus on the right, this one, so we're with this expression, right? This minus should say no rotation. To say no rotation is false. So no rotation is false. The operator to the right is minus, so therefore this is false, and this is false too. Therefore, we jump to the else. When I jump to the else, we perform the rotation. this rotation was correct before. So again, result right equals right left. Right left is result. Result right is right left. Right left is result. So this was correct previously. Why is it no longer correct? So it didn't rotate. Why didn't it rotate? Why didn't it rotate? Not rotate. Why? What? Which means that there's a oh, I forgot to change this one. All right. 10 minus 2 minus 1, 7. Finally. What did we want to change to try and the one that had more, right? More than so we have to go back to the leftmost. And let's get rid of this one. So 10 minus 2 minus 1. Okay, so the terminal has crashed. I hope it's not a machine. No, the machine is fine. Okay, terminal has crashed. Oh, okay. Well, you're going to go through this when you're debugging your own code. So, all right. So, all right. So I'm going to add another guard here. we're going to do the following. If so if this happens, it shouldn't matter. Right is leftmost right. So this should not change in case we have only two levels. So I can't remember which one didn't work. Yeah, I think if you want to go, feel free to go. Did this one work? No, it didn't, right? I don't want to crash the terminal again. It didn't work, right? So since we have only two levels, what we're expecting is that no, but it didn't work because it produced a cyclic tree, right? It didn't work when we tried to print the tree. It wasn't when we actually rotated the tree, right? So but then the evaluation will go into infinite loop as well. So what I want to find out is printf. I'm just going to call it condition %d backslash n. What I want to find out is if the result, if right equals. But this is not correct because it has a single level. But if it has a single level, so if n left is null, return n. Right? So this assumes we're going to go, there are at least two levels in the tree. But when we have a 10 minus 2 minus 1, right, the leftmost tree, right, that we're trying to rotate actually has only one level. The rightmost tree, it only has one level, right? So we're trying to rotate this 10, so minus, we're trying to rotate this 10 minus 2, 1, right? We're trying to rotate this, and we're saying this is the right, and then give me the leftmost of the right. But this assumes there are at least two levels. If there's only one level, then if there's only one level, no, so there are two levels. So there's a left. In which case I would be returning n anyway. Anyway, this doesn't. It's defensive in the sense that if it's wrong, and we want to find out whether right equals leftmost of right, and I'm just gonna do a system that I'm gonna do an exit one here. So 10 minus 2 minus 1. So the condition is 1, which means that this is true. Right? Which is what we want. So this works. But we don't want leftmost to right. We want leftmost to right left. Actually, I would like to say left here. Unfortunately, it doesn't work in C. So we have to do struct node star temp equals leftmost right, and then we can say TMP. Okay, let me explain. I do get the left. I do get the leftmost. In this case, what is the leftmost? It's exactly this guy, right? When I printed out and it was a 1, just that's what I verified, right? But what I want to do is move this guy here, right? So I get the leftmost, arrow left to move here. Make sense? Right? So in this case, right, I need the 10 to move here, right? In this case, I need the 10 to move here, right? So what am I going to do? I can't move the 10 because then I don't know, what I need to do is put something here, right? And that we haven't done either. That's not about. All right. So then what I'm going to do is result.left becomes leftmost, arrow left. Right? So this is what we're doing. TMP is the leftmost, and result right becomes leftmost, arrow left. Right? Then leftmost arrow left has to become result. But that we haven't done either. We left it. So instead of having result left equals right left equals result, this has to become TMP. So that should fix the minus, and then we're going to do the division. 10 minus 2 minus 1. Let's make sure that now we're losing completely the 10. Result right, TMP left. Why did I say TMP equals result? TMP left. And minus 2 minus 1, 7. And 10 minus 2 minus 1 minus 3, 4. And 10 minus 2 minus 1 minus 3 minus 4, 0. Okay, so it's finally working. And then, so let's call this TMP something more suggestive, LFTMST. Sort of looks like leftmost. All right. So the next thing we do is Control C this. Is there anything specific to plus or minus? No. Go here. and do the same. So now let's pick a number with a lot of divisors. 144 divided by 3 divided by 2 divided by 3 divided by 2. The result is 4. Seems to work correctly. Okay, let's combine them now. So let's produce 144 through subtraction. So 200 minus 50 minus 5 minus 1 divided by 3 by 2 by 4 and by 3. The result is 2. And it seems to work correctly as well. Okay, I think now it's correct. Okay, so I think, did you understand the rotation part? That's the most subtle part here. So actually, initially I didn't want to have to try to fix that, right? But then I said, what the heck? You're not going to see, if you don't see it now, you're never going to see it. So you might as well have the experience. The interesting thing that we sorted out today, however, is the way we are reading the numbers, right? So fixing the numbers was relatively easy, right? And yeah, if it had worked with a simple rotation, I think that would have been marvelous and would have been a perfect class. Unfortunately, as I was thinking of the algorithm, I didn't realize that it wasn't correct at the time, so we only discovered that in class. But in the end, we got to fix it. So what I'm going to do is I'm going to give you this code as it is, but then I'm going to give you a cleaned up version, right? Which would be, yeah, a bit more, professionally developed. There is a lot of repetition, right? So this if is very similar with the other if, right? So this typically doesn't happen. And as we developed the program, it was relatively easy. It was easier to understand by actually expanding the code and not creating a lot of functions. But what typically would happen is that we do extract these similar codes into functions, and then we try to reuse code, and that results actually in a smaller program, right? But then it is a bit more difficult to understand because you have to go back and forth between functions to understand what's going on. So you're going to have both versions, and take a look, and potentially, try to use it to expand it to something, right? So maybe add a power operator, or maybe add a factorial, or maybe add unary or unary plus and minus, so you can get negative numbers. Okay. Questions? I'm sure you can't wait to leave the room. Anyway, questions? No, go. What are we waiting for? See you next time. Thanks for putting up with